A signal is periodic if it repeats itself after a fixed interval. Mathematically, y of t equals y of t plus t for all t, where t is the period. Periodic signals are everywhere in engineering: power line voltages, clock signals, and carrier waves in communication systems. But how can we construct a periodic signal from a basic building block? The answer is simple. Take a signal and create shifted copies of it. Here is the key formula. Given any signal x of t with finite duration, we can create a periodic signal by summing shifted copies. Y of t equals the sum from k equals -infinity to infinity of x of t minus kt. Each copy is shifted by a multiple of t. If t is greater than the width of x of t, the copies do not overlap, and y of t is simply a repeating pattern of x of t with period t. This is the most basic way to construct periodic signals. Let us see this in action. Consider x of t, a symmetric triangle signal with vertices at -1, 0, 0, 1, and 1, 0. Its width is 2. If we choose t equals 3, which is greater than 2, the shifted copies will not overlap. We place copies at t equals 0, 3, -3, 6, -6, and so on. Each triangle sits alone, separated by gaps. The result y of t is periodic with period t equals 3. We can also combine scaling with shifting. Consider y of t equals the sum of x of the quantity t minus kt0 divided by capital T. Here, we first stretch x of t by replacing t with t over capital T. This gives x of t over t a wider version of the original signal. Then, we create copies shifted by multiples of t0. As long as the stretched signal fits within one period, meaning its width is less than t0, the copies do not overlap and y of t is periodic with period t0. Let us visualize this. Starting with x of t, our triangle signal spanning from -1 to 1. First, we stretch it by replacing t with t over t. With t equals 2, the signal x of t over 2 now spans from -2 to +2. Next, we create copies at intervals of t0 equals 5. Since the stretched width of 4 is less than t0 equals 5, the copies fit without overlapping. The resulting y of t is periodic with period t0. Now, here is the interesting case. What happens when the copies do overlap? Consider our triangle x of t on the interval -1 to 1 and set t equals 1. The copies x of t minus 1, and x of t plus 1 all overlap. In the region from 0 to 1, x of t equals 1 minus t, and x of t minus 1 equals t. Their sum is 1 minus t plus t, which equals 1. The same cancellation happens everywhere. The infinite sum y of t equals 1, a constant. The overlapping triangles perfectly fill in each other's gaps. What if we only sum 3 copies instead of infinitely many? Let y of t equal x of t plus x of t minus 1 plus x of t plus 1. From t equals -2 to -1, only x of t plus 1 contributes, rising from 0 to 1. From -1 to 1, the overlapping copies sum to exactly 1, forming a flat top. From 1 to 2, only x of t minus 1 contributes, falling from 1 to 0. The result is a trapezoid with vertices at -2, 0, -1, 1, 1, 1, and 2, 0. Let us wrap up Lecture 1. In Lesson 1, we learned individual signal operations, shifting, scaling, and reversal. In Lesson 2, we combine these operations using the two-step method for x of at plus b. And in this lesson, we learned to construct periodic signals by summing shifted copies. When copies do not overlap, the result simply repeats x of t. When they do overlap, the sum can produce surprising results like a constant. This completes our introduction to signal manipulations. In the next lecture, we will explore system properties and classifications.